Hello, Math 1224. This is Dr. P with Lesson Launch 19.2, the longest inch. So in this video, I want to talk about how we might have known that the actual error of this estimate that we did in the last video, this estimate for e squared, isn't that big. We got an actual error of 0.12, meaning that the actual value of e squared was our estimate, 7.27, plus this error, 0.12, so that came out to 7.39 and change. Okay, so that's what it means for the error to be 0.12. So in this video, I kind of want to do something that is hard to do in teaching, and that is wind back the clock to sometime before we knew that, that the error would be 0.12, because remember, in order to find that out, I had to use Wolfram Alpha. And the whole point of this estimation technique is that I should be able to find some bound for the error of my estimate without having to use anything more sophisticated than the Taylor series methods that I've been using here. Okay, so that's the goal. So to do this, we're going to need something called Taylor's theorem. And the way I'm presenting this is a little bit different from what's in the Hughes Hallett textbook, so you might want to take a look there as well. I think what's there is a slightly simplified version of what I'm doing here. Now, Taylor's theorem is a little bit different from the idea of a Taylor series, although the two are extremely related. Okay, Taylor's theorem basically says this. By the way, in doing the research on this, I saw that there are several different versions of Taylor's theorem. This is what I would call the Lagrange version, and you'll see that name in the textbook if you take a look there. So this is called the Lagrange error estimation theorem. Okay, so Taylor's theorem says this. Suppose that f is differentiable infinitely many times. Actually, for actual Taylor's theorem, differentiable infinitely. It's hard to talk and write at the same time. So suppose f is differentiable infinitely many times. I was going to say the theorem doesn't actually require infinitely many times. It requires a certain number of times, but really everything we're going to do in this course, the functions are going to be differentiable infinitely many times anyway. There's no real trouble in assuming that. Okay, now let's suppose I have a Taylor polynomial of degree k. Actually, let's not say degree k, let's say degree n. I'm going to use k as the index of summation later. A Taylor polynomial of degree n centered at x equals a. Okay, so I'm going to give the general version of this, even though most of what we're going to do in this video and the next one are going to be centered at x equals 0. All right, so I got a Taylor polynomial degree n centered at x equals a. And I want to use this. There we go. I want to use this Taylor polynomial to approximate f at x. So this is x is some specific input, okay? All right, so here's the theorem. By the way, let me give a little bit of a visual of what's going on here. Just want to make sure that what I'm trying to do here is somewhat clear. So I've got some function, right? This is a cartoon of the function f of x equals e to the x. Okay? And I have a Taylor polynomial centered at some point a. So a is where this Taylor polynomial is centered. And then there's some other point x where I want to estimate the value of f of x. But all that I have is a Taylor polynomial, which might go something more like this. Let me use a different color for this. There we go. So maybe I got some Taylor polynomial that goes like that. All right? And I want to know what the error of this estimation is going to be. So how far off this curve is from this one. That is, how far off these two are from each other. Okay, that's the error I'm trying to find. And in this picture, the error is going to be positive because the actual function is in dark blue and my estimate is in light blue. Okay, so anyway, I want to approximate f of x. Okay, so here's the theorem. The theorem says there exists some number, I'm going to call it t, in the interval from a to x such that the actual value of f of x is equal to my nth Taylor polynomial evaluated at x plus the following thing, plus the n plus 1th derivative of f evaluated at t over n plus 1 factorial times x minus a to the n plus 1. All right, so I know that when I first saw this theorem, this was confusing as all get out. So I'm going to try and just situate all this in the problem that we're trying to do here. Okay, so recall, this is what we're trying to estimate here. This is the actual value that we are trying to get close to. That's the actual value. Our estimate is this thing. This is our estimate. We're estimating using the first n terms or so of the Taylor series, or up to the nth degree term. And then this thing here, this is our error term. And this is the thing that we're trying to get a handle on here. We want to figure out how big that could be. Now, one thing I want you to notice here is that this thing here, it looks a heck of a lot like the next term of a Taylor series, right? Like this Taylor polynomial here, this thing here was, just as a reminder, this was f at a over 0 factorial times x minus a, to the 0, plus f prime at a over 1 factorial times x minus a to the 1, and so on up to f nth derivative at a, I'm going to need a bigger boat here, at a over n factorial times x minus a to the n. Okay, so what we're looking at here, this gadget here, kind of looks like the next term, except there's a key difference. The key difference is that there is this value of t, let's get this where we can see as much as possible here. There's this value of t here, somewhere between a and x, and that's all we know about it, is it's somewhere between those, such that if I substitute the n plus 1th derivative at that t into this formula here, substitute that derivative in at t, divide by n plus 1 factorial, multiply by x minus a to the n plus 1, I get, for some reason, exactly the right error. And that's crazy. And there's actually, that by the way, actually is crazy. I know that we've been using the word crazy quite a bit the last couple of days, but that is legit crazy. Okay, that is cray-cray to the max. So I'm not going to try and prove that that's the case. I'm not going to try and explain why that's the case, although I will mention that this is a cousin, this whole theorem here is related to the mean value theorem, which you covered in, I hope covered in theorem, there we go, covered in Calc 1. The mean value theorem is actually essentially the version of this when n is equal to 0, because in that case, this term here becomes something involving the first derivative. You could actually work out what happens with this formula, or this equation, when capital N is 0, and see that it's exactly the mean value theorem. So this is really an extension of the mean value theorem, and it can be proven using the mean value theorem in mathematical induction. We're not going to do that here. I just wanted you to know that this is related to something that we know. Okay, so anyway, that's the error term. So now I want to use that to figure out how big that error could be in that series that we talked about earlier, this e squared. All right, so we're going to use Taylor's theorem to estimate the error for our estimate of e squared. Okay, so last time we said, in the last video, we said that this e squared is approximately equal to this sum of terms here, and that's 7.27. So how could we use Taylor's theorem? I wonder if I could drag this around. Can I do that? Oh, not without taking a whole bunch of other stuff with me. Okay, so we'll just copy this over here then. So I'm going to try and estimate the error for e squared approximately 1 plus 2 over 1 factorial plus 2 squared over 2 factorial plus 2 to the third over 3 factorial, etc. You get the idea. So here's how we do this. So we're going to use the Lagrange error estimate The Lagrange error estimate says there is some t in the interval between where my series is centered. Now remember that series is just e to the x equals the sum k equals 0 to infinity of x to the k over k factorial. The fact that I've got powers of x and not x minus some other constant, that tells me that my center is a equals 0. That's where this thing is centered. So there's going to be some t in the interval between that center and the place where I'm trying to estimate f, which is 2. So there's some t in between those numbers such that the error is the next derivative, so that's the sixth derivative of f at t, divided by 6 factorial times x minus a, so that's the difference between these two numbers here. Remember, this is x, this is a. So 2 minus 0 to the sixth. Okay? Now, what is f sixth derivative at t anyway? The sixth derivative of f is just e to the x. Every derivative of that, including the sixth derivative, is just e to the x. So this error here is just going to be e to the t over 6 factorial times 2 to the sixth. And remember, t is some number between, let me do this over here. T is some number between 0 and 2. Okay, so the question is, how big could this be exactly? Well, how big could this be? Well, the maximum that it could be would be whatever makes this number here, this e to the t, whatever makes that the biggest, subject to t being between 0 and 2. So that would be e squared, because e to the t gets bigger as t gets bigger. Now the thing is that the premise of this whole problem was I didn't know what e squared is. I didn't have a value for that. I have an estimate for it, but I don't know how close that estimate is. So is there anything intelligent I could say about e squared that would help me to pin this down a little bit, that would tell me that I have some bound for how big this is? Well, I know that I recall from my previous knowledge that e is definitely less than 3, which means e squared would have to be something less than or equal to 9. I'm just going to say less than or equal to, because I'm going to use that to estimate what e squared at most would be. So the biggest that this could be would be 9 over 6 factorial times 64, which comes out to 9 over 6 factorial is 720. So this gives me, I think, 74 over 80, because I'm canceling out the 9 with this 720 here, which gives me about 0.8. So I know that whatever happens, my error is going to be less than or equal to 0.8. All right? So that means that whatever happens, I know that this estimate that I got back over here, whoops, wrong button. This estimate that I got back over here, when I did this sum here, got 7.27, I know that the actual value of e squared has to be less than or equal to my estimate, 7.27, plus this error term of 0.8. So e squared is going to be somewhere between what I got, 7.27, and that plus 0.8. Now you realize that is not an especially not an especially efficient bound, because we said that my actual error is like minimal. It was a 0.12, and I said that my error could be as large as 0.8. But that's the thing about this, is the Lagrange bound doesn't necessarily tell us exactly what our error is going to be. It just gives us some ballpark in which it has to sit. Okay. But one thing that you can take to the bank now, even if you don't have a calculator, even if we hadn't been able to do all of this, is that no matter what, that error is going to be less than or equal to 0.8. And we know that because of this Lagrange bound from Taylor's theorem here. Okay, so just as a quick review, what we did was we first calculated our estimate. So we calculate our estimate, and we write that down. So we estimate using a Taylor series. And then we looked at this Lagrange bound for the error. And then the Lagrange bound doesn't tell us exactly what the error is. It tells us that there's this mysterious t in between the center for our Taylor series and where we are trying to estimate f. Somewhere in there's a t for which the next derivative of f at t, when substituted directly into this formula, gives us the exact error. And then finally, we analyzed, let's see, what other color do I have here? I guess this is it. And finally, we said, how big can that error be? And for that, we just had to know a little bit about functions, because we were looking at this possible error of e to the t. Remember, that was the sixth derivative of f at t. So we said, okay, this error term has to contain an e to the t, where t is between 0 and 2. Worst case scenario, that t is a 2. And then we said, well, I don't know what e squared is exactly. That was sort of the whole point of this thing. But I do know that it's less than or equal to 9. So know that the error can't be any bigger than what it were if there were a 9 there. So that would give me 0.8. And I said that's the maximum error I could have. That's not necessarily the error. In fact, our error was quite a bit smaller than that in actuality. But that gives us a bound. Okay, so I realize there's a lot going on in that video. You might want to just give this one another watch. I know this is kind of a long one, but you might want to just walk through the steps again. And I'm going to do one more video later and illustrate the process on one more function, so stay tuned.